Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I will start off by giving an example that combines the idea of translation and reflection. And then afterwards, I will be talking about the idea of dilation. So for the first example here, example 6.16, you are required to represent this graph here using a mathematical equation. You have to write down the equation for this graph, and based on this shape of the graph, this is quite similar to the basic function which you have seen in the previous video, which is y is equal to modulus or absolute value of x. And this graph is simply a straight line, v-shaped, where the minimum point is at 0, 0, something like that. So this is x, this is y. So this shape here could be our starting point. So our first step, you can imagine having this graph somewhere here. So the next step is, I hope you can see that the pink graph here is somewhere towards the left of x-axis. So I need to somehow move this graph towards the left. And how many units should I move? The number of units should match the point given here. So it will be at -4. Therefore, for the second step, I need to introduce x plus 4. So by doing this, I will be moving this graph 4 units to the left. So this can be visualized as such. Okay, so something like that. Okay. Now, next, I hope you can see that there is some sort of gap in between this point to x-axis, which is not given by this graph that I have right now. So I need to introduce another term. Okay, so I'm going to introduce another number, another factor to this expression that I have here. So that would be y is equal to absolute value of x plus 4, and I want to move it 3 units up, so plus 3. So I'm moving it 3 units up to match the position of this point here. So 3 units up is 1, 2, somewhere here 3. So the graph will look like this. Now, I hope that you are able to see that this pink graph here is just the reflection of this graph along this x-axis. Okay, and this graph is given by this equation. Now, how do I get the equation for the pink graph? Obviously, I have to introduce negative sign on outside of this whole function here, so that this whole function will be reflected along the x-axis. So negative sign outside the whole function, so the function is absolute value of x plus 4 plus 3. So that can be finalized as absolute value of x plus 4 minus 3. And this is the equation that is used to describe this given graph here. Alright, now let's move on to the idea of dilation. Basically, this is about stretching or shrinking the graph by multiplying the basic function with some numbers. For example, if let's say my basic function is y equals to fx, and if I multiply this with a factor c, so c is outside the original function, so c is outside the original function, therefore the graph will be vertically stretched. Now if I factor it with if I multiply with a factor of 1 over c, the graph will be vertically compressed. So when the factor is outside the function, you're talking about either stretching or compressing vertically. Now, if the factor is inside the function, which is next to x, so this is factor 1 over c next to x inside the function, then the graph is horizontally stretched. And if I have the factor here, factor c, you multiply x with factor c inside the function, then this is horizontally compressed. So the graph will be horizontally compressed. So I hope you can see that when the factor is inside the function, then you are talking about either stretching it horizontally or compressing it horizontally. Now let us look at some simple exercise related to sketching. So I hope you can see that this is the original graph where y is equal to x squared. Excuse me, x and y squared, x and x squared. So this is y is equal to x squared. So this is the graph given here. Now on this graph, we're going to sketch another two different functions. So the first one is the factor is outside the function. Outside the function, that means we are talking about vertical, and in this vertical stretching or compressing, and in this case this is about vertically stretching. So vertically stretched. Okay, you have a function, you have a graph that will be vertically stretched, and for this one, this is the graph that will be horizontally compressed. Okay, so first let's look at this one first. Okay, you can imagine the change in the graph based on selecting several points. So for example, when x is 0, so y will also be 0. 0 squared times 2 is 0. Now if x is -2, originally when x is -2, this function, the output is at 4, but now the output will be at 8. So maybe somewhere here. So the same thing for when the value of x is 2. Okay, so originally it is at 4, but now with the new function here, it will be multiplied with factor 2, so it will be somewhere here. So for example, if you have 4, originally it will be at 16, and when you multiply 2, it will be somewhere on 32, which is outside range of the graph given here. Okay, so anyway, we can actually get the idea now, so we can just like sketch the graph. Okay, maybe somewhere there. Okay, so never mind, so just sketch the graph. is something like that. This is actually ugly, but I think that will do. Anyway, let's move on to the next function. So 2x squared. Oh yeah, before that, I hope you can see that this original point here is stretched vertically. So this point is also stretched vertically. So that's the idea of this one being vertically stretched. Now let's look at the second function here. So when x is 0, it will be somewhere here too. Okay, that maintains at y 0. When x is 2, the value will be at 16. So when x is negative 2, the value here will also be at 16, somewhere here. And so the graph will be looking slightly like this. Maybe. Okay, it's to the inside. Okay, and I hope that you can see that originally we have at this point 416, and now it is horizontally compressed towards point 216. Okay, so the same thing for this one. It is horizontally compressed and the graph is going towards inside. Okay, now let's look at the next example here. So in the next example here, you have y is equal to half x squared. So notice that 1 over 2 here is outside the original function. That means you're talking about vertically compressed. Okay, and this one is 1 over 2 is inside the function itself, so this will be horizontally stretched. So now let us do this function first. So again, when x is 0, y is also 0. Now when x is 2, the original value is at 4. Negative 2, the original value is at 4. But now for this function, it will be compressed to a different value, which is 4 over 2 is 2. So it will be somewhere here. So it will be somewhere here, and this will also be somewhere here. Okay, now similar to this one, if x is 4, and the value of the new y here will be at 8, maybe somewhere here. So this is at negative 4, will be maybe somewhere here. So then our graph will look like this. Okay, right. Now I hope you can see that this is being vertically compressed. So it is going downwards. Okay, this one is vertically compressed. You are like pressing it downwards, compressing it downwards. Now let's look at the second function, purple. So for this one, you can see that when x is 0, y is also 0 at the same point. Now, when x is 2, then the value of this y will become 1. So it is even lower than that, lower than this point. So it will be somewhere here. So this one is 2, so it will be like somewhere here. Okay, lower than that point. Next, if this is x is 4, then this will be at 4 over 2 is 2, to the power of 2 is 4, so it will be at this same point, this one, and this one will be somewhere here. So you can see that this is even flatter, the curve is even flatter than the red curve, so it's really flat. So something like that. So it is being horizontally stretched. So if this is the original point, it is being stretched horizontally. So this is the original point being horizontally stretched. Okay. Now, these are some other examples where you can see that the original function is given by the red line. So red curve is the original function, and this one is the function being vertically compressed. So you can see that you're compressing from, if it's here, you're compressing it towards this direction, and this one will compress it towards this direction. So you're compressing at the top and at the bottom, you're compressing it, so it becomes this blue curve. Now for this one, this is the original function, and you can see that this graph is multiplied with a factor 6. So this is being vertically stretched. So at point 0, it is maintained as it is, but all this point is stretched upwards. This is being stretched. The same thing for this one. This is being stretched. You can imagine it being stretched in both directions, upwards and downwards. So this is some examples related to vertically stretching and compressing. Now I hope you get the idea of dilation, and that's the end of this video. I will see you in the next video, which will give you some examples related to combining all these ideas. With that, thank you very much for watching. I'll see you again in the next video.